now let's go to our first gas law. The first gas law is called Boyle's gas law. And Boyle's gas law is pretty simple. It is the idea that you're studying pressure and volume. And pressure and volume have the same similar relationship, but here we'll talk about a balloon back here with this material on the outside and the inside. And so what happens? And what happens to the volume? The pressure changes. So let's think of it this way. Let's say we have the situation where we have a balloon and we put it into a container. Or let's even go back to the mountain idea. We have our balloon down here at the lower level, and we know that the atoms are on both sides. We have a pressure outside, we have a pressure inside, and so the balloon is at a steady state. Okay? Collisions. But as we go up in the mountains, we know that our balloon now is going to end up having less particles around it. So the pressure inside is not the same as outside. The pressure effect is greater. So the balloon is going to increase in size because it has more pressure inside than outside. So the system can actually increase. So what Boyle found out when he studied gases was that as the pressure decreased on a system, the volume would increase. And so they were using it to study balloons and that other kind of things. But he also found out as you lower the balloon into a lower atmosphere, the pressure increased, and so the balloon on the inside couldn't push out. It got pushed closer together. So as the pressure went up, the volume went down. And that kind of relationship is called inverse. It's when two things act in an opposite direction. So Boyle's law is an inverse relationship. Okay? And so we write his law in a unique way. We say that pressure times volume equals pressure times volume in the new situation. Okay? And so that helps us to figure out how Boyle worked out his law when he studied pressures and volumes. So that gives you a quick example. The next law is Charles' law. Charles' law is by another scientist who studied temperature and pressure. Temperature and volume. And when he studied temperature and volume, he studied different changes. So let's take the same balloon. We now have a balloon, and it has particles inside that are moving around at a certain speed. So we have our speed idea over here, and we know that as they're bouncing around at a certain speed, they do generate a certain pressure. Okay? But if I begin to heat up the balloons, let's say our temperature goes up, then these particles are going to move faster. The faster they move, the more they collide against the side, and so at a higher speed, we get a larger volume. So as the temperature goes up, our balloon expands. That was the same example we talked about earlier when you're talking about putting an inner tube or something like that, or a beach ball in the sun, and then it begins to expand. But as you take that balloon and put it into a freezer or that cooler weather, then it ends up shrinking and being soft. Okay? So temperature and volume. So as the temperature goes down, our volume will go down. Charles discovered that it was the exact same directional change. We call them, or we call this relationship, a direct relationship. Direct just means to change in the same way. As one goes up, the other goes up. As one goes down, the other goes down. Mathematically, that makes it a little bit different. Mathematically, it changes the equation to look like this. Which means we would take the temperature and we would divide it into the volume, and then we would take the new volume and put the temperature on the bottom on the other side, and then that way the relationship would be steady. So we have discovered Boyle's law and Charles' law. Boyle's law is inverse, Charles' law is direct. The last scientists, or set of scientists, was a group of gentlemen named Gay-Lussac. It might have been one, but I believe it was two. And so they studied temperature and pressure. Okay? So we've all been experienced, they've always been told never to throw a can or sealed can into a fire. That's because if you take a can, which of course has volume, and you have a bunch of trapped materials in that can, if you put it in a temperature change situation, those particles will move faster, so the temperature goes up. Particles move faster, you get more collisions, but the system cannot expand, so the volume can't change, so the pressure and the number of collisions begins to increase so dramatically that the wall can fail and the can can explode. So temperature goes up, the pressure inside goes up. Okay? And then of course if you take the flame away, then what happens is your system begins to cool down, and as it cools down, the temperature cools down, and then the pressure also cools down. That is also another direct relationship. And so when that happens, we know we can study that again, and so then we look at our laws. In our last direct law had a division in it. Well, then this one's going to also have a division problem in it. And when he took his and studied this law, they found out that the pressure and the temperature related in this way. So we have another law where we have a direct relationship. Okay? That seems like a lot of math in a lot of ways, but we found a really good way to put all three laws together. Okay, so we've condensed our formulas over here. We want to introduce a quick little formula that actually helps you remember these better. We're going to write down what is called the combined gas law. And the combined gas law is really simple. It just takes all of these laws right here and it combines them into one. So we're going to write P1V1 over T1 equals P2V2 over T2. Now, the 1 and 2 are really not anything different. It just means that we had a condition, we had a system, and we changed it. Maybe we changed the temperature, so now there's a new temperature. So did the balloon expand, or did it contract, or did the pressure go up, or did the pressure go down? So this is just two scenarios. And this combined gas law came from putting all of these three laws together. So, as an example, we can see right here, Boyle did not write a law that had temperature involved. So if I take this combined gas law and I remove the temperature, then I have Boyle's law. So we just have to remove that law. And if I go over to Charles' law, we can see he didn't study or didn't write a law on pressure. He just did volume and temperature. So if we remove the pressure, we can see that we have Charles' law. Charles' law is right in there, but you just have to remove the pressure. Okay? And then we go to Gay-Lussac's law, and we see they didn't study the volume. So if we remove volume, we then have the Gay-Lussac law. So really, all three laws have been combined into one gas law. Okay? And so this is the best one to remember. And when you use this law, it's easy then to do the math. And we're going to go on from there. But before I go on in the math, I do need to stop and talk about temperature and pressure and volume. Okay, back here we mentioned temperature and pressure. We've been doing temperatures at degrees Celsius. Okay, we talked about Kelvin. Well, the combined gas law is very specific. Temperature cannot be done in degrees Celsius. It must be done all the time in kelvins. And we remember that our equation change is adding 273 to any Celsius number, we'll put it in Kelvin. So all temperatures in the combined gas law, or these gas laws here, must be in kelvins. Okay? So that's a standard condition. We can't do it any other way. And because we do that, gotta remember, we're gonna have a problem because if we use 0 degrees Celsius, 0 in any of these problems gives us a 0 answer. And that's not acceptable because gases do exist when it is actually 0 degrees outside. Okay? The next problem we run across is pressure. In chemistry, there is multiple units that are available. Just like we can do grams or pounds, and sometimes we have Fahrenheit, there is different scales that are being used around the world still in chemistry. And those three temperature scales are millimeters of mercury, and these are considered standard conditions, meaning a normal room condition. There is atmospheres, and there is kilopascals. And we run across them in our textbooks in so many different formats. Our book that we now have likes to use millimeters of mercury and atmospheres. But the nice thing about no matter which one they use, if they give you millimeters or atmospheres, you just simply, whatever answer you get for that pressure is the unit you put after your number, okay? So these are the three gas pressures that can be measured in. And so we run across them, and you will see them at different times. It's okay. It doesn't matter. You don't have to have it in one or the other, but in temperature, it must be in kelvins, okay? So from there, next time we start the video, we'll talk about how to actually do the math.